majority of this review is just filled with diagrams from Kelper because they have really good diagrams as it relates to how the stuff are shown. And I'm gonna be just going through that really. So generally the qualitative analysis, we know that these are just confirmatory tests, right? Well, they are really presumptive tests that we're looking at, right? So the first of the tests that we tend to look at are the flame tests, right? And how well the flame tests are really done with cations, right? We know that metals themselves, right, can give off certain colors when under extreme heat, right? So what we tend to do for the flame test, right, we tend to use something like a wooden splint, right? We soak wooden splint in in a solution, right, of high concentration of the said ion, or we use a nichrome wire, right? And we put the nichrome wire in a solution of the ions and then we place it into the flame, right? So the general flames that we tend to look at here, right, are given here. Generally just 5, right? So the sodium, now we know that when we put sodium into the specific flame, the sodium is gonna burn with a bright yellow, right? So it's like an orangish yellow color, right? Potassium itself would burn with a lilac flame, or some people would say a purple flame. Lilac, purple, you can use it interchangeably, but I would prefer if you use lilac, right? Calcium would give a straight red flame, right? So calcium would burn red. Copper and barium, right? Barium tends to give a great green color, while copper gives an apple green, right? A slightly brighter green color than that of barium. And lithium, as well as scandium, would give a crimson red color, right? So there are slight differences with some of them, and some of them are huge differences, all right? So these are generally the flame tests that we look at. Flame tests are not very common; they're really uncommon, right? On past papers, right? But these are general flame tests that we really look through. No questions, no concerns. All right, just drop a 1 in the chat if we're ready to move on to the next slide. All right, lovely. So let's move on. So the test for our cations, the syllabus asks us. So, well, it wants us to have the ability to identify magnesium, aluminium, calcium, chromium, manganese, iron in the 2 oxidation states, zinc, copper, barium, lead, and ammonia, right? When reacted with a base, right, alkali, which is hydroxide tests, right? When reacting with carbonates and when we're reacting it with ammonia. Now, there's one section that I don't think I've well, it's probably in, right? But carbonate specifically. When we react a metal and a carbonate, what happens?
You get carbon dioxide gas.
Right, so carbon dioxide gas is a good indicator that we have reacted a metal with a carbonate, right? Or we could have reacted an acid with a carbonate, right? But acids, right? We're not really looking at acids, so we would know that it's one of the metals, right? So metals with carbonates will give us that carbon dioxide gas. And how do we test for carbon dioxide gas?
Bubble through
Lime
lime water.
Bubble through lime water, all right. Any other test?
So it should
Link.
out a lick flame.
Okay, all right, lovely. So somebody said lime water, somebody said sodium bicarbonate. All right, that could be one. We could use well, we know that lime water is calcium carbonate. Is it calcium hydroxide or well calcium carbonate, right? What is lime water? Calcium carbonate or calcium hydroxide? Which one?
Calcium carbonate.
Calcium carbonate. Lovely. Right. So with that carbon dioxide, we can also use a glowing splint, right? If it holds a glowing splint, then that would be carbon dioxide, right? So looking at the reactions, right? The first reactions we're looking at is the cations with sodium hydroxide, right? So when we make a solution of the compound and distill the water, what we're doing is releasing the cations into solution, and now we add sodium hydroxide dropwise. If you add dropwise, you should get a white precipitate for aluminium, calcium, lead, and zinc, right? But you'll get a blue precipitate for copper, iron 2 plus will be green, right? And iron 3 plus would be red brown, and there will be no precipitate for ammonia, right? But when we add now in excess, right, we're going to have a precipitate now form with calcium. Know that calcium, right, will form a white precipitate in with sodium hydroxide, and generally in excess as well. It will be completely insoluble, right? Copper and the iron, right, will remain there, right? Will just remain completely insoluble, while the precipitates for aluminum, lead, and zinc will dissolve. All right. So with a small amount of sodium hydroxide, all will form precipitates except for ammonia. Ammonia will not react generally like that, right? Because it's two bases you're mixing. You're mixing sodium hydroxide and ammonia, right? So there would be no general reaction there, but all will form precipitates. The only ones that will dissolve in excess would be aluminum, lead, and zinc. All right. So that should be fine. So these reactions are some things that after a while in chemistry you just know, right? You just look at it and you just say, all right, this is aluminum. Like you can just figure it out, right? So let's have a look at this now. Note that you can't really distinguish between aluminum, lead, and zinc, and that's what we're going to be doing. In other tests now, we can actually distinguish aluminum, lead, and zinc. Can anybody can propose tests that we can use to distinguish aluminum, lead, and zinc when they're in the solutions like that? How could we
For
distinguish?
lead, you can use the halides.
Which halide we tend to use? What are the most common halide?
Iodine.
Right, so the potassium iodide solution, alright? How could we distinguish between aluminum and zinc? No. Because lead will be yellow, aluminum and zinc will be colorless. So how would we distinguish between aluminum and zinc? Alright, I want us to find an answer to that. Alright, while we go through. Okay. So when we react them with no ammonium hydroxide, so reacting them now with ammonium ions, we're gonna do the same thing, create a solution, right? Dissolving our cations in solution. Then we add sodium ammonium hydroxide in this case, dropwise. Calcium will not react, right? So calcium will not react. So if you add something to the calcium ions and it forms a precipitate, that means you have add sodium hydroxide to it, not ammonium hydroxide, because it forms no precipitate with ammonium hydroxide. Then we're gonna have precipitates forming with our general aluminum, lead, zinc, copper, and our iron, right? And we know our different colors of our transition complexes, right? Um, our copper ammonium, right? Our exoamino copper will be blue. Our exoamino iron 2 plus and our exoamino iron 3 will be green and red respectively, right? And then in excess now, our iron precipitates will remain insoluble, but our aluminium and lead will remain insoluble as well, right? And our soluble precipitates would be copper and zinc. So this is how we distinguish between zinc and aluminium. So if we have compounds here and we react them with sodium hydroxide, right, and we get different soluble different solutions on excess, right? So they are not precipitates, but in excess they actually dissolve, right? And they have no color. We can distinguish them by adding potassium iodide to see if lead is present, or we could add the ammonium, right? And if it remains as a precipitate, it is aluminum. If it dissolves, then it is zinc. So that is how we distinguish between the aluminum and the zinc there. All right. So all it is just a series of reactions, and we must know the outcome. All right. So everything here should be fine. Any questions or concerns?
So you can go back over the results for aluminum and calcium.
Aluminium and calcium. Okay, so for calcium specifically, calcium will form a precipitate, right? Whether or not it's in a small amount of sodium hydroxide or excess sodium hydroxide, but there will be no reactions that we can see here with the ammonium hydroxide, right? But with sodium hydroxide, it would react to form an insoluble precipitate, all right? So that is what's happening there. But for aluminium now, right? Aluminium will form a soluble precipitate, what soluble in excess, right? It's soluble in excess, right? Sodium hydroxide, but insoluble in excess ammonium hydroxide, right? So that's the difference between the two, right? The thing with zinc now, zinc is soluble in excess sodium hydroxide, and it's still soluble in ammonium hydroxide. So that's how you can determine whether or not this colorless solution is aluminium or zinc. That's how you can distinguish between them. Right? But notice using sodium hydroxide or ammonium hydroxide, the aluminium and zinc is still not, so we still don't know the difference between them because both of them are colorless. Right? This should be here. Let me just fix that real quick. Right? Just fix that real quick for you guys and then reshare. Alright. So because it was in the wrong place, let me just reshare the presentation. Alright. So looking at this now, we can determine whether or not it's lead, right? If we use potassium iodide, right? And then we know that aluminum won't form a precipitate with potassium iodide, but lead will, right? So we have that there. So that is really the series of tests that we go through to figure out all of our cations, right? Generally that we need to look at, right? The thing about the chromium and the manganese, why chromium and manganese isn't placed there, right? Is because we generally know, right, the color of chromium 3 plus and manganese, right, 2 plus. You guys should know those oxidation states that will give the different colors, right, in redox reactions as well as transition metal complexes. We use them time and time again, so you guys would know those, right? But the major issue is these different ions, okay? So that is really for cations. Is there anything else that needs going over for cations? Everything here is fine, right? Okay, so drop a one in the chat if we're ready to move on to anions, right? I want to make sure everybody's fine with the cations. So if I were to ask you, right, I have a solution of ion A plus, right? And I react it with sodium hydroxide, right, to gain an insoluble precipitate, right? An insoluble precipitate, a colorless insoluble, well, a white precipitate, right? Insoluble precipitate with excess sodium hydroxide, right? But with ammonium hydroxide, I get a clear solution, right? A soluble precipitate on excess ammonium hydroxide. Could you guys tell me what that ion is?
Sir, do you mind repeating?
And let me repeat. Okay, Denicia has an answer, but let me just repeat before Denicia goes, right? I want you guys to raise hand if you can answer, by the way, right? So we can have some order. But if we have a cation A, right, that is insoluble with excess sodium hydroxide, right, to give a white precipitate, right, and it is soluble in excess ammonium hydroxide to give a clear solution, right? What is that ion that we're talking about? Denise has an answer. Go ahead.
Good morning,
Good
sir.
morning.
I believe the answer is calcium.
Calcium. Interesting. Okay, it's kind of a technicality because calcium would not react, right? So it cannot form a soluble precipitate in the ammonia. You get what I'm saying? So it wouldn't react overall. So it's a great guess because technically it will remain clear because it's not gonna react, right? But we're talking about a soluble precipitate. So it will form a precipitate and then it's gonna be soluble, alright? Let me see. Anybody else raise their hand? Let me just check real quick. Oh, go ahead. Go ahead, Silbad.
Sir, would it be zinc?
It would be zinc. Lovely. Alright. So probably somebody stated in the chat as well. So it would be zinc specifically, right? So it's just understanding that. So sodium hydroxide specifically, right? If we react it, we're going to get a precipitate, right? Soluble precipitate, and ammonium is going to remain that. All right. So that should be fine. So if we have the test for the anions now, let me check the chat real quick. What is happening here? All right, so for the anions now, right, upon heating, right, let's look at these anions, the carbonates and the well, the nitrogen gases, right? So with a small quantity, right, of them, of the solid, right, in a test tube, right, if we have a carbonate, right, and we heat the carbonate, what we're going to be getting, right, is carbon dioxide being involved, right? A specific substance, right? So the gas test specifically. If we heat something, right, and we can see that a white precipitate is formed with lime water, right, then it would be carbon dioxide gas being released, right? That makes sense. Okay, so we heat the carbonate specifically and we get carbon dioxide and some oxygen ions as well. Okay, so here now, if we are looking at the sodium, well, not, why am I saying sodium? All right, so if we look at the nitrogen oxide, right, if we have this here, right, we're going the NO3 gas, right, when bonded to sodium or potassium, oxygen will be evolved and oxygen will relight a glowing splint. That is how we can tell, right? So if it relights a glowing splint, then it is possible that oxygen being evolved, and this anion in question would be NO3 negative, right? Right? If it's bonded with to metals, calcium and below in the reactivity series. So if you react with less reactive metals, right? If it's bonded to less reactive metals, nitrogen dioxide, right, itself will be evolved, right? Nitrogen dioxide gas and oxygen gas would be evolved. So we're gonna get a brownish gas, and we're gonna have a gas that relights the glowing splint, right? So what gas we're releasing is actually nitrogen dioxide in that case, right? Which is brown. Nitrogen trioxide generally wouldn't give a brownish color like that, right? So if we're bonded to more reactive metals such as sodium and potassium, we know that these two metals are extremely reactive, right? It will actually give off oxygen gas, right, and keep the NO2 bonded to it, right? So you're going to have the advent of something like a potassium nitrite or a sodium nitrite. But in the case of something less reactive, we're going to have the nitrate, right, actually going to be given off, right? Then it will be decomposed into nitrogen dioxide, which is brown, and oxygen, which can relight a glowing splint. So hopefully that information makes sense. So looking at the equations here. All right. So especially when we get our qualitative analysis tables, go ahead. I think somebody unmuted their mic.
Sir, can you go again, please?
All right. So especially, let me just complete the start and then go again. Right. So especially when we get the qualitative analysis tables, they ask you to give the color change and an inference. Right. Most times, people would like you to write the color change, what you think is causing the color change. So what anion, what gas is giving that color change, and then we would probably like you to write the reaction that is occurring that would produce said compound or said derivative that will give that color or that whatever reaction that is, right? So what we're saying is that carbonates generally, we know from module 3 chemistry, right? Module 3 states that our carbonates are low, right? Are low in thermal decomposition, right? So it requires a low energy to decompose carbonates. And we know that because of the polarizability of our cations, right? When we start going through the periodic trends, then we look at that. But our carbonates are generally things that really decompose under high temperatures, right? What we're doing is heating the ions, right? So if you heat a carbonate, it's going to release carbon dioxide, it's going to decompose, right? So we're gonna decompose to get carbon dioxide, and we're going to get that calcium hydroxide precipitate in calcium carbonate solution, right? So we're gonna have that. We're gonna get the calcium carbonate. Lime water. Can you guys remind me what lime water is?
Calcium carbonate.
Okay. I haven't used lime water in a while, right? So each time I say calcium carbonate, it kind of it's calcium hydroxide, isn't it? Is it the calcium hydroxide? Because I'm here saying carbonate, I'm like, something feels off.
Oh, sorry. Apologies, sir. It is calcium hydroxide.
Okay, here people here gaslighting me. It's calcium hydroxide, and then it will actually form calcium carbonate, right? Which is insoluble. It's calcium hydroxide is lime water, please. Right here being gaslit. All right, so we have that there, right? But what we're talking about with the nitrates now, our nitrates generally are a little bit more stable, has a little bit more thermal stability. Right, so what we're looking at with our nitrates here is that if we react our nitrate with some reactive metal, when we decompose it with heat, we're going to have oxygen gas being prepared, right? While the nitrate ions, right, nitrite rather ions, will remain in solution, right, or generally remain bonded in some cases, right? So here we have the reaction of our nitrate decomposing to produce that, all right? Oxygen. But in the case here now, when it's reacted with calcium and below in the reactivity series, we're going to get nitrogen dioxide gas being evolved and the oxygen as well. So we can actually react the gas to the glowing splint, right? To see if it is relit, right? Rather, with a glowing splint. But more than likely, if we see the gas, we're going to know that it's brown and we don't need to really test with the glowing splint, right? But if it's brown, we know that it's a mixture of it is caused by nitrogen dioxide, and usually it's a mixture of nitrogen dioxide along with oxygen. All right. Now the the nitrate ion now, when reacting the nitrates now with concentrated sulfuric acid and copper turnings, right? We must look at the fact that they will actually have a solution that turns blue and a brown gas is evolved. What is happening? We're reacting sulfuric acid with nitrates. Sulfuric acid and nitrates will give you nitric acid and sulfates, right? You should know that nitric acid and sulfates. And now when the copper is going to displace the hydrogen on the nitric acid to give us copper nitrate solution, which is blue, because copper 2 plus ions are now present in the solution, and the copper nitrate, the copper displacement of the nitric acid, right, will actually give us nitrogen dioxide gas, right? My brain froze. So nitrogen dioxide gas. So this is the reaction we're seeing here, right? So sulfuric acid will react to our nitrate to give us nitric acid and sulfates, right? Sulfate would generally be the spectator. We're not really doing anything with the sulfate now, right? Those will be free ions in solution. Now the copper is going to react now with the nitric acid that was produced to give us copper nitrate, which is blue in solution. Well, I have to specifically say copper 2 nitrate, which is going to be here in the solution like that. And then we're going to have our nitrogen dioxide gas coming off as a brown gas and water being created. So here, when we react a nitrate with sulfuric acid, we get nitrogen dioxide gas coming off. Right? That is fine. Fine so far. All right. So let's have a look now. Let me just check something real quick before we look at it reacting with dilute acid. All right. So, oh my gosh. All right. So reacting with dilute acid now. If we react with dilute nitric acid or hydrochloric acid, these two things, right? So these two derivatives will most likely show, right? We will have carbon dioxide because we're reacting a carbonate with an acid. It would give us carbon dioxide and water, right? We know that from CSEC chemistry. But what's happening now, right? If we have potassium manganate, right? So potassium permanganate in a solution and react with an acid, what's going to happen is the oxidation reaction, which will change the oxidation state of manganate, right? So what we're going to have now is a purple to colorless solution with the production of sulfur dioxide or sulfur trioxide gas. Well, it will be sulfur dioxide most likely, right? How can we tell the presence of sulfur dioxide? How can we tell when sulfur dioxide is present?
So the smell?
The smell, right? The smell of sulfur dioxide is terrible, right? So you're going to know the smell. A pungent smell would be the source of that, right? So we have that there, right? And we also have manganese, right? It's gonna change from purple to color. It's purple. When it's purple, what oxidation state does manganese have? When it's purple,
Sir, is it +4?
+4. Interesting.
Is it +7?
+7. All right. So the color of +4, right? Do we know the color of +4 though? So you said that it's going to be purple, right? +4 is actually a brownish black color, right?
Um,
Go ahead.
sir, +3.
+3. Oh, hold on. All right. So manganese, right? So let's look at the manganese specifically. So manganese, we're saying +4. +4 is going to be a brown black color, brownish black color, right? BLA. This doesn't BLACK. The writing for this is terrible. Manganese 2 plus. What is that? Or well, it would technically be +2. The oxidation state +2 will be what? A slightly pink color, right? A pale pink, right? Manganese 3 plus though. Somebody said 3 plus. The color of 3 plus, right? Isn't that like a purplish color? It's going to be purplish, you know. Manganese 3 plus is actually purplish. The purplish red color, purple red, right? Manganese, sorry, let me and manganese would be 6 plus, and manganese 7 plus. What would be manganese 6 plus or +6? +6 is the oxidation state, 6 plus is the charge. But we know that charge is equal to oxidation state, we should know that. Manganese 6 plus is going to be green, right? And manganese 7, right, no, is going to be purple. So it's a manganese, right? So we have a manganese rainbow here. It's kind of a rainbow. So manganese 2 plus is pink, then 3 plus is purplish red, 4 plus is brownish black, 6 plus is green, 7 plus is purple. But usually we see it in its 7 plus form, right? Going back from 7 plus to 2 plus. We usually see that those oxidation states, right? But in this case is gonna be a palish, well a color, well it's gonna be a purple color, right? And then it's going down, so it's going to be actually technically it won't be 4 +4 here, right? What this is showing here, right, is just the reaction of the ion specifically. So it's most likely going to be a +7, right? It's most likely going to be +7 or +3, right? But in the syllabus we normally use +7, so I'm assuming that usually in your scenarios a purple manganese would most likely be +7. All right, so we have that there. Reactions with concentrated sulfuric acid now, right, for everything else. So we know those two that are focused on, the carbonate and the sulfates, right? With chlorine now, we're gonna get white fumes, right, when we're reacting it with ammonia gas, right? So we're gonna get we're gonna get chlorine evolving when we react with when we react chloride ions with sulfuric acid, we're gonna get hydrogen chloride reacting, right? Coming off, right? And hydrogen chloride, we know when we react hydrogen chloride with ammonia, we get ammonium chloride, which is a white fume, right? That has a pungent smell, right? Chlorine tends to have a greenish color though, right? In very, very high concentrations, right? So we have that there as well. So when we have chloride ions being produced and hydrochloric acid being produced, it is colorless. So what we can do now is react with ammonia gas to see if a white fume appears, which is ammonium chloride, right? And we should remember that from the ring spot lab that we looked at in, is it a rate lab or a diffusion lab in CSEC chemistry? You had that lab there, all right? Bromine, now we know that bromine is a red brown gas. Most persons tend to know that, and most persons tend to move on because bromine tends to be a red brown gas. It seems like it's just a household reaction. Everybody knows that. And then here now, a gray black solid forms, which sublimes to form a purplish vapor. Right? Remember that iodine sublimes. Right? So what we're going to have is an iodine precipitate, an iodide precipitate, which is usually grayish black. Right? And then in that precipitate will now sublime into a purple vapor, which is gaseous iodine. Alright, everything is fine there. Everything lovely, right? So we have the observation, and we have the ion, and we have the gas evolved. This is all the information you need. Alright? So let's move on. Okay, before I move on, are there any questions? Just drop a numeral 1 in the chat if you're ready to move on. Alright? So drop a numeral 1 if you're ready to move on. So I can know that everybody's fine and there are no questions being asked. Alright. Okay, so one person. Okay, so we're ready to move on. Here now, we're going to have the reaction of our anions with silver nitrate, then aqueous ammonia. So when we react, right, we're going to dissolve the solid in silver nitrate, in nitric acid first, right? We dissolve in nitric acid first, right? And then we add a few drops of silver nitrate. And here for our halides, we will see that chlorine will form a white precipitate, which when reacts in sunlight gives a purplish gray color. Because as we know from rates of reaction, light can increase the rate of a reaction, the rate of a decomposition, or any type of reaction like that. But the sunlight would actually change, right, the color of the precipitate to a purplish gray for chlorine. With bromine, we're going to have a cream precipitate being formed, which turns slightly green in sunlight. And for iodine, we're just going to have a pale yellow precipitate being formed. And this is when we react our halides with our nitrate, well, silver nitrate, right? So react with silver nitrate, that's what happens. So we add the nitric acid, and we know why we add the nitric acid. We add the nitric acid to take out any other type of ion that may interfere, right? So we use it, right, to get all the ions free in solution, and then now the silver present now can now displace the metals, right, within these complexes, right, or within these ions, and form the silver chloride, silver bromide, and silver iodide. So silver chloride is a white precipitate that turns purplish gray in sunlight. Silver bromide is slightly green in sunlight, but generally it's a cream precipitate, and silver iodide is yellow all year round, right? Now when we react these silver halides now with ammonia, we tend to get different precipitates now, right? We get white precipitates, right? So what's happening here now? With our silver chloride, our precipitate dissolves, forming a colorless solution, right? And what's happening with the silver bromide now, we get a partially dissolved precipitate. So it's a slightly insoluble or sparingly soluble solution, or precipitate rather. So it's sparingly soluble, right? And then with the silver iodide now, it does not dissolve. Alright? So we have those now. So we add our silver nitrates, right, to our solution of our halides with dilute nitric acid, and we get these precipitates, right? And when we add ammonia now, what's happening now is that the solubility, right, of silver halides in ammonia increases as we decreases as we descend the group, right? So silver fluoride will be more soluble than silver chloride, which is more soluble than silver bromide, which is more soluble than silver iodide. That's what we have there. Any questions, issues, concerns to tackle? If not, let me know if we're ready to move on to the next slide. All right, so Shadi is ready to move on. All right, so I'm not hearing any questions or concerns, so let us move on. Identifying the sulfate ion now with the reaction of barium nitrate, then dilute acid. Go ahead.
Is it
Is it?
is it true that complex ions are formed when
Fine.
aqueous ammonia is added to the halide?
Okay, hold on. Okay, let me. Okay. Complex. You're saying that complexes are formed when ammonia is added to halides? Halides? That's what you're asking?
Yes, complex ions.
Okay, ammonia is a ligand, and the halides are also ligands. Ammonia is a compound, and the halides are nonmetals. I won't see how a complex ion can be formed unless it's something like an ammonium iodide, etc. Um, so probably there's a possibility for that to occur. Probably it's a possibility. I've never looked at it.
Okay.
All right.
Okay.
So identifying sulfate ion now, we have to react with barium nitrate, then the dilute acid. So when we have now a solid dissolved in water, we add a few drops of barium nitrate or barium chloride, right? And now we're looking at the precipitates that are formed. So what we can have is barium carbonate, which is a white precipitate, right? Barium sulfate, um, so barium sulfates, right, would be barium sulfite and sulfate will be white precipitates as well, right? So you have to look at the SO3 2 plus and the SO4 2 plus. So this trisulfide, well not trisulfide, the sulfur trioxide, right, and the sulfate, right? So let's have a look at this now. When we actually react these now with nitric acid or hydrochloric acid and heat in order to increase the rate of reaction, right, we're going to look at the different types of what happens to the precipitates, whether or not it dissolves or whether or not a gas is evolved, right? So let's look at this now. So when we do that to it now, the barium carbonate now will actually release carbon dioxide when you add it with an acid and heat it. You know, acid and carbonates give you carbon dioxide. So that's honest. That makes sense, right? With our trisulfide now, what's not our trisulfide, our sulfur trioxide, right? With that ion now, we're gonna have the precipitate dissolving, and then we're gonna release sulfur dioxide, right? And we know that our sulfur dioxide itself, um, we can know what that is, right? There's a gas test that we'll look at, right? And then looking at the sulfate ion now, that's gonna have a precipitate that remains. So the precipitate actually remains, and then we're gonna have no general reaction with the dilute acid. So that's basically it. Right, so with our sulfate, it's going to be insoluble. With our trisulfide ion attached to our barium, it's going to dissolve, giving off sulfur dioxide, and our carbonate will give us our gas, right? And this links to what we know about group 2 sulfates, that group 2 sulfates decrease in its solubility as we descend the group. We should know that about our group 2 sulfates by now. All right? Okay. Does anybody know a special use for barium sulfate? There's something that we use barium sulfates for. Using X-rays. It's used as dyes in the body, right? That then can be highlighted through different types of medical procedures. So it's used for marking, right? Usually for different types of laparoscopic procedures, etc. Right? Or using for X-rays as well. Okay, so gas tests now, the last sets of tests. You should know our gas tests. So identifying our common gases now, oxygen is a common gas, very, very common. We know that it is odorless and colorless, therefore we can note the presence of oxygen by the relighting of a glowing splint, right? And this is because oxygen contributes to combustion, so the heat is going to increase, right? So we're going to have the glowing splint relighting into a fire, okay? For a hydrogen gas, also colorless and odorless, therefore we usually use it, right, with a glowing splint to give a squeaky pop. And that's because when the hydrogen reacts with the oxygen, right, that is through the combustion of that lighted splint, right, we're going to have an explosive reaction occurring as hydrogen and oxygen becomes water. So here is the equation of the formation of water. And if anybody can remember from energetics, the enthalpy change of this reaction will be the enthalpy of formation of water. Alright? Slightly. It would be slightly because this is in gas and the water should be in liquid. Alright? So it's going to be similar to the enthalpy of formation, but not exactly. Alright? So we're going to have an explosive reaction there, which is the squeaky pop that we get, and then the flame will be extinguished. For carbon dioxide, which is also colorless and odorless, we're going to have a white precipitate when bubbled through calcium hydroxide, right? And the precipitate calcium carbonate redissolves on continued bubbling, right? So if you do that, it's gonna redissolve as calcium hydrogen carbonate is formed, which is actually soluble. So some people get really confused because some people think that calcium hydroxide and carbon dioxide should give you calcium carbonate, which is true, which is insoluble. But some people think that if the scenario says that it redissolves upon continued bubbling, people think that that is no longer carbon dioxide. It is actually, but we just have hydrogen carbonate being produced, all right, which is soluble, all right. So moving on to our this HCl. HCl actually has a sharp acidic odor, right, and it is colorless, and we can note the advent of this gas, right, or know that that smell is contributing to this gas when we react it with ammonium with ammonium gas or ammonia, right, in a glass rod to produce white fumes, right? So ammonia and hydrochloric acid will give us the ammonium chloride that we're seeking there, which is a solid. So two gases will react to give a solid that will be clear. You could see it clearly in the air, all right? So these things are actually really useful, you know. So if you're gonna go into chemistry or any type of chemical-based industry or job, right, or career area, these things are really important, right? Because I remember a day in my lab when I was creating nickel chloride, right, complexes, and finding out the concentration of the complexes. We had to use ammonia for something, right? Everybody was running from the back of the lab, don't know what that smell is. It's burning people's eyes. All you have to do is release a little hydrochloric acid, and you see the white solid being formed in the air, and we know that its ammonia has been released, right? So all you do is just secure all the bottles with ammonia, right? So simple things like that. So these gas tests are actually really, really useful. All right. So here now we have ammonia, right? Ammonia has a pungent odor as well because ammonia is usually the gas that comes from decomposition of urea in urine. So it's that smell, right? So you can use moist litmus paper, and if it turns blue, we can know that it's ammonia because ammonia is a basic gas, right? And we can also have, you know, white fumes with hydrochloric acid. So if it works with if ammonia reacts with hydrochloric acid to give us white fumes, right, hydrochloric acid should be able to react with ammonia to give us back the white fumes. So it's generally the same thing, right? Or we can use litmus paper. So with chlorine as well, chlorine in high concentration is a yellowish green color, right? And it has a sharp choking odor, and we can tend to use a moist litmus paper, right? And it should turn red and then it bleaches to white, and that's how we can tell whether or not chlorine gas has been has evolved, right? So that's how we know if that gas being produced is chlorine. And if we have sulfate, now we know that sulfur dioxide here rather, sulfur dioxide has a pungent smell, a very disgusting odor. And if we react it with acidified permanganate, we're going to get a purple to colorless solution. And if we react it with potassium dichromate, we're gonna get an orange to green solution, right? So we have to know that. we're going to have a reduction. Well, we're going to have oxidation reaction, redox reactions occurring, right? So the sulfur dioxide, it reduces the purple permanganate 7 plus ion to the 2 plus, and with the sulfur dioxide with the dichromate now, it reduces the orange 6 plus ion, right, to our 3 plus. So we have that information there. With our NO2, we know that's a brown gas, and it has actually has a irritating odor as well. It in high concentrations, it can actually burn, right? So we have that there, and what happens, if we have a blue litmus paper, it will turn red because it's an acidic gas, and that generally means that if we bubble nitrogen dioxide through water, we should get nitric acid, and we can test the pH of that solution, and that should be able to give us our red litmus change, right? Or whatever, with whatever indicator you want to use, right? So nitrogen dioxide is a brownish gas with a sharp odor, right? It can turn a blue litmus paper to red, moist blue litmus paper to red, right? And if all of that is done and you still are not sure, you can bubble it into water and actually test the pH, right? Water now is colorless and odorless, and in order to test the presence of water vapor, we can use cobalt 2 chloride paper, right? Because we know that cobalt chloride is a complex, right? Cobalt tetrachloride is a complex, right? We should remember that. Tetrachloride is a complex, right? And when we react with water, we're going to have ligand exchange, right? And then the cobalt is going to become hexa aqua cobalt in a complex, and hexa aqua cobalt is pink, right? So if you have cobalt chloride paper, which is blue, it will turn pink in the presence of water. Or we could use anhydrous copper sulfate, which is white, and then when you dissolve, when anhydrous copper sulfate comes in contact with water, it will become blue, as we have the releasing of the copper 2 plus ions, right? So that is it for our gases. So that is generally it for qualitative analysis. We just generally have to know our reactions of our flame test generally, right? Which is there. Our tests are cations with sodium hydroxide and ammonium hydroxide. Then our tests for heating, right? Some of our anions, right? Our nitrate ion test, right? Reactions with dilute nitric or hydrochloric acid. Your reactions with concentrated sulfuric acid. Your silver
Sir.
nitrate complexes with your iodide. Go ahead. I'm just summing up what we did in this entire thing.
Yeah, could I see the cations table again, please?
The cation table. Let's look at the cation table. Which one? Sodium hydroxide or ammonium hydroxide? Both. So this is sodium hydroxide,
Yes.
and then this is the ammonium hydroxide.
Sorry, I think questions still confuse me now because insoluble in two of them. I did say insoluble in questions. So how is it zinc?
Oh, I said insoluble in the question?
Yes, sir.
Oh my apologies.
Yes, sir, that's why.
Oh, I misspoke. My apologies. If I said insoluble, oh my gosh, that's my apologies. My apologies there. Alright, should have been soluble in both. Right? So the question that I was mentally asking, right, is if we have a solution, right, that is actually soluble, right, like insoluble rather, in ammonium hydroxide, but in excess ammonium hydroxide, but actually soluble in excess ammonium hydroxide, that would be aluminum to zinc, right? That was probably I misspoke. Probably I said sodium hydroxide instead of ammonium hydroxide, right? So probably that's what I said. But we have the information and we should be able to get the right answers, right? From the different questions that may be asked of us. So those are all of the reactions that you look at. This is just another table of the test for anions that was in this slide as well. Just a tiny table, summarized table. There's less information that what was on the previous slides. It's just a little sum up here. Alright. So that is it for our qualitative analysis review.